Welcome to the webcast, Spot Welding Techniques. This webcast will discuss how to properly perform spot welding techniques that simulate what is done at the factory. You will learn how spot welding, in conjunction with adhesives, weld bonding, can help protect against corrosion. For more in-depth content on spot welding techniques, ICAR offers a live training class. Today's presentation will be led by Jeff Poole, Performance Training Coordinator at ICAR, the leader in collision industry training. I'm Bruce Adams, Managing Editor of ABRN, and I'll be the moderator. We'd like to thank our sponsor, ProSpot, for bringing this webcast to you free of charge. Please note that at the end of today's presentation, there will be a question and answer period where you can submit written questions. Now let's get started. Jeff, can you tell us how we got to where we are now in terms of welding?
Sure, Bruce. I'd like to just take a moment and thank you and the folks at ABRN for making this possible, as well as the folks at ProSpot for sponsoring this. Over the years, the welding processes that we've used in collision repair have changed. And one of the main influencing factors is really the evolution of the materials used in the vehicles. Construction has changed dramatically. And we look back over the history of automobiles, and for the first 70 or so years, we didn't see any dramatic evolution in the material content. But then about the 70s and going into the 80s, and right around when ICAR was founded, we really started to see that transition with the materials getting thinner and lighter and stronger materials going in there as well. The oxyacetylene welding process was accepted for a lot of years, and it was okay on the heavy gauge mild steels that we had at the time, but again, there was a lot of excessive heat there, and controlling that heat effect zone on these thinner steels and the effects of that heat on the high strength steels was really detrimental. So that was a major challenge for us. Around that same time, there's a stick arc welding was the mainstay of anything that was heavy gauge, like on frames and things of that nature, and controlling that heat was rather challenging as well. At a certain point, MIG welding was introduced to the collision repair industry, and it very quickly became the favorite preferred welding method for the industry. It gave us a lot more control over the arc and a much smaller heat effect zone relative to oxyacetylene or stick arc welding, and so that's where MIG welding really came in to be for so many years as our preferred method. Another welding method that we see limited application of right now in the U.S. is the MIG brazing process, and this uses lower heat input and doesn't melt the base metal. It's more of an adhesion process. It's not a fusion process. It does use a smaller heat effect zone, or create a smaller heat effect zone, if you will. Decrease the amount of corrosion protection that's burned away. MIG brazing does require a larger footprint than MIG welding. This helps ensure joint strength. As we take a look at some of the different steels used in today's vehicles, we have such a wide variety of different materials going into today's vehicles. In years past, we had mild steel as the mainstay. Then slowly we started to see the high strength and the ultra high strength steels come into play. Within the past 5 to 10 years, in reality, we've started to see other steels creep into that picture. And predominantly in the last 5 years, we've really seen a huge onslaught of the dual phase steels and the advanced high strength steels that have additional manufacturing properties, but more importantly, they've got additional occupant protection properties. And as we're evaluating the repair process and we're formulating our repair plan on that vehicle, we have to look at the amount of these advanced high-strength steels and ultra-high-strength steels and what the effects of heat input from the welding process are. That's a primary consideration.
What are some of the differences between the welding processes?
It really comes down to equipment, the operation of the equipment, and depending on the welding process, the technique. Really, the biggest goal, one of the biggest factors that we look at is how can we get that weld done the quickest with the least heat input and get a good weld that has the integrity we're looking for. Heat input's a big factor. So the appearance is also a consideration. Again, stepping back, MIG welding was leaps and bounds ahead of oxyacetylene welding so far as minimizing that heat effect zone. And resistance spot welding is leaps and bounds ahead of MIG welding so far as minimizing that heat effect zone. Now, throughout this presentation, I'm going to try to stick with using the terminology spot weld. Some folks may call it resistance welding or resistance spot welding, or you may hear squeeze type resistance spot welding out in the industry, or the acronym STRSW for that. As we take a look at the screen with the temperature readings that we're looking at here, we've got one photo that shows a MIG plug weld that was just done, and we're taking temperature readings pretty close to that MIG plug weld. And then we have another photo there with a resistance spot weld that was done with an inverter technology machine, and we're taking the temperature near that weld location as well. And we're seeing a dramatic temperature difference. You may not be able to see the numbers on the screen, but close to the MIG plug weld, we've got 581 degrees on the non-contact thermometer. And close to that spot weld with that inverter technology machine, we've got 74 degrees Fahrenheit. So this really speaks volumes for helping to minimize that heat effect.
Thank you, Jeff. Now I would like to ask the audience a polling question that they can respond to online. Their responses will be tabulated and presented to all viewers. Our question is, how many shops have spot welding machines? Please select one of the following answers. We don't have any. Yes, we have one. Yes, we have two or more. Or I don't work in a shop. Once again, the question is, how many shops have spot welding machines? Please answer, we don't have any. We have one. We have two or more, or I don't work in a shop. And we're going to wait a minute here while the technology catches up and presents the answers to everybody. Okay, we can see that 42% of the shops have one spot welding machine, 15% don't have any, and actually 13% have two or more. Very interesting. Now I would like to ask the audience a second polling question. Once again, please respond to this online, and the results will be presented to all viewers. This is based on the result of the previous question. If you answered that your shop has a spot welder, is it single phase, three-phase, inverter, or hybrid battery? For those of you who answered that your shop has a spot welder, is your spot welder single phase, three-phase, inverter, or hybrid battery? Please select one of those four answers, and we'll be able to see in a very short period of time where we are on that. Okay, nearly half have three-phase, a third, slightly more than a third, single-phase, and only 11% inverter, 5% hybrid battery. Thanks very much for sharing that information with us by polling in with your answers. Hey, Jeff, what are some of the typical spot welding applications?
Bruce, whenever spot welding equipment first came to the collision repair industry, much of the equipment was, I'm going to say, borrowed from the sheet metal industry and was really designed for working with very light gauge materials and making a relatively small resistance weld. So early on there was limited acceptance of the applications, but I really have to say over the years the equipment manufacturers that have come to develop, do the testing research and evolve this equipment, it's come a long, long ways. And as we take a look at today's applications, it goes beyond exterior body panels. It goes beyond just cosmetics. We're finding where in some situations it's acceptable to use this equipment on some of our structural components, pillars, rocker panels, rail flanges, and things of that nature. It's going to be critical no matter what type of welder we have. We want to make sure that we identify the correct weld testing procedures and do destructive testing, and we're going to discuss this closer to the end of the course, but this becomes a critical element. No matter how good the technology is, we need to still come back to our basic roots and do that destructive testing to validate. The spot welding process also is not recommended for aluminum during collision repairs at this time. Spot welding aluminum requires substantially higher currents than steel. But the reality is we really don't have to concern ourselves too much about that, because the vehicle makers that may have applications out there where they spot welded on the assembly line, which is few and far between on an aluminum structured vehicle, they've identified alternative means to repair those vehicles, typically either MIG plug welds or using some sort of a rivet bonding process. Moving forward, we're going to take a look at some additional aspects of spot welding. It is the main OEM welding method. This is a process that's relatively easy to learn. It is important that we understand that it's not necessarily as simple as just pulling the trigger. We need to understand what we're doing when we pull that trigger, so it does require some training. And a lot of this training will become very equipment specific whenever it comes to that actual piece of equipment in the shop setting. But it's typically easier than MIG welding. The original appearance and integrity in most cases can be duplicated. And again, this is definitely a plus for the customer and for that end product. I've seen situations where I've gone into shops and I've looked at installations of core supports and other components on vehicles, and it's impressive. I think back to the days of the number of components that I welded in using MIG plug welds and dressing the welds and all of that went along with that. It's just like I dreamed about equipment like we have today. It's a process that really creates minimal sparking. We don't have to drill any holes, so there's, I want to say, a little less prep. We still have some preparation involved, but it saves on drilling or punching holes with like we do with MIG welding. We don't need any filler metal or shielding gas. So as we look at some basic safety aspects, we should have a full face shield or safety glasses with side shields for the technician operating the equipment. And as we look at some additional preparation, typically we need to have access to both sides of the panel. Those contact tips have to be able to come together and squeeze that metal together to allow that current to flow. In some cases, we may have some recommendations or limitations on combined panel thicknesses that we can weld. Again, that would be an OEM guideline that we'd be looking at, and it's really important that we're accessing those with every repair.
Can you tell us what happens when you make a resistance spot weld?
There's really three stages to the spot welding process. It's an electric pressure welding process. So in a nutshell, we have stage one. We have the squeeze time. That's where we've got our panels fit up, and we take and we position our equipment, and we press the button, and the contact tips come together, and we apply pressure. Those tips apply pressure to that panel. They have an air cylinder in that equipment typically that takes and applies that pressure through the mechanism. So we've got that pressure in stage one, squeeze time. Stage two is where we really see differences between the different technologies out there. But again, in a nutshell, the current on time, this is where in stage two, the equipment turns on the power and the current flows through the weld. This is generally only for a fraction of a second. And again, depending on the technology and the equipment, it may be longer or slightly shorter. But during this current on time, that current flows very easily through the arms of the equipment and through the electrodes of the equipment. But when it hits the steel has higher electrical resistance than the arms and cables and electrode tips of the equipment. So that resistance in any electrical circuit where we have resistance, we get heat. So that resistance in that steel causes heat, and there's enough heat generated due to that current flowing through there to melt that metal. The pressure of those tips then takes and squeezes that metal together essentially, and it fuses. That metal fuses together. The last stage, the hold time, this is also a really important stage, because really during this stage, those contact tips maintain contact with that weld site location, and the current is not flowing anymore. At this point, those contact tips are actually soaking heat out of the weld. This becomes something important to remember later on when we talk about different cooling systems, because there are some advantages to some of the different types of cooling systems.
So understanding power sources is critical when you're selecting spot welding equipment.
It certainly is, and again, we may see some challenges in some areas with the different power that's available and some limitations that we'll take a look at. Some of the basic options for spot welding power sources include our single phase, which is the top diagram, our three-phase, which is the center diagram, and then direct current, which is typical what we'd get out of storage batteries in the bottom diagram. Just really quick, taking a look at the top diagram there. Depending on what country you're in, most of the folks are probably North America that are listening, but I know that we may have some folks from out of the country. Here in the United States, we've got 60 hertz power, or 60 cycles per second. Other countries may have 50 cycles per second, but I'm going to work with 60 cycles per second because that's easy math for me. Envision I'm a boxer, and as a boxer, I have the ability to punch you 60 times in 1 second. That's pretty impressive. Okay, now I'm a single-phase boxer, so I can hit you 60 times a second. Now envision I'm a three-phase boxer. I can hit you with my first phase, and then my second phase, and then my third phase, all within the same time frame, essentially in succession. So I have the ability to, within 1 second, hit you 180 times. So if I'm a three-phase boxer, I'm punching you 3 times as much in that same time frame. That's pretty impressive. And whenever we come down to the direct current, that's just a constant on once we pull the trigger and the current's flowing. So that's pretty impressive in itself. As we move ahead to slide 10, it is important, and it's really critical for this equipment. I've seen situations where we've set equipment up in facilities, and then we found out, it's not performing to its full potential. And so some education here is in order. It's really, really critical that we consult with an electrician, but what's more important about that is that electrician truly understands the instantaneous load draw of some of this equipment. It's substantially different than just an electric motor like on a compressor or something of that nature. So this is where it's going to be really important to make sure that we're testing the available voltage and current at each outlet, and typically while the equipment is actually under load, because this is really going to spell out where we're at.
What about shops that only have single-phase power?
The equipment in reality is going to function as good as the power available. Something that I want to kind of reinforce here, and something that I'm very aware of, is some of the equipment suppliers that sell this resistant spot welding equipment. They have the ability to come in and use a line load tester. And what they'll do is they'll hook this equipment up to your facility power, and that'll analyze the capability of your facility's power, see if it's up to the job. In some cases, we see there's a necessity to upgrade the facility power and the wiring, and this may lead out to the pole, out off the street, or however it's supplied to your facility. This can be pretty significant in some cases. In situations where we only have single-phase power, single-phase equipment is available. The single-phase equipment typically doesn't have all the bells and whistles of, I want to say, some of the three-phase or the inverter equipment that's available. But taking a look at a typical scenario with a piece of three-phase equipment, we have what we call a primary and a secondary circuit. And our primary circuit, that's the power coming in from our power panel or out of the outlet. And then we have our secondary circuit, which actually is the weld circuit. And so with this, we have high voltage coming in on the primary side, and then we have our transgun or transformer unit that then takes and steps that down to low voltage, but at very high current required to make that weld. As we take a look at slide 13, where we have situations where three-phase or other primary power challenges may exist, the battery-operated equipment that's been developed in many cases is capable of up to about 10,000 amps to produce spot welds. Again, this equipment doesn't typically have all the fancy bells and whistles of the inverter machines and some of the three-phase machines that are out there. But if we're in a situation where we're really severely limited on power availability, here we have equipment that can take and facilitate those welds using storage batteries. This equipment does need to plug in and recharge, typically off 110 or 220 volt AC power. But this might be a solution for folks that may have some unique challenges on power distribution in their area.
Can you talk to us a little bit about inverter technology?
The inverter technology equipment is, I'm kind of a technology junkie. I like to understand it. I like to know how it works and why does it work better, or why is it, I want to say a step up from something else. And what we have here with this equipment, and again, it really depends on the specific piece of equipment to exactly what it does and how it does it. But again, in a nutshell, kind of in a basic format, what this equipment can do is take that 50 to 60 hertz AC power coming in, it puts it through a rectifier which changes it to direct current. And it takes and filters this, it'll send it through a switching circuit. Through this switching circuit, it's cycled on and off very rapidly to create high frequency. Now, what's important to understand about high frequency is more efficient in most cases to work with than our 50 or 60 cycles. So with this high frequency, it's then sent through a transformer to create low voltage, high current. In some cases, we've got units out there exceeding 12,000 amps in current capability. One of the major advantages of high frequency power source is it's capable of greater control. We've chopped this up and we've given it a much finer dilution, if you will, to take and then modify it, work with it. And this takes and gives us a lot greater control over the weld parameters. It also supports substantially better information feedback. Some of this equipment, as it's making the weld, it's monitoring what's happening in that weld, and the equipment can actually modify what's happening with that waveform. So this type of technology in some cases operates in excess of 1,000 cycles per second. Gives us much finer control of the output current, in most cases a smoother, more consistent output current. So again, there's some huge advantages here. Inverter welders, by and far, achieve shorter weld times than other types of technology out there for the most part, and this is really good news for the heat-sensitive steels. Using my analogy from the single-phase and three-phase, if I'm a single-phase boxer, I'm hitting you 60 times in a second. And if I'm a three-phase boxer, I'm hitting you 180 times in a second. If I have an inverter welder working at 2,000 cycles or 2,000 hertz, I'm packing 2,000 punches into that same 1 second. That's very formidable. Something else that we want to keep in mind, of the vehicle makers that recommend specific equipment, what we've noted is that most of the welders that are recommended have the inverter technology.
How does the electrode tip design play into the resistance welding process?
We essentially have an electrical circuit on the secondary side of that equipment, and the electrode tips are made of a copper alloy. These electrode tips have very low electrical have very low electrical resistance and very good thermal conductivity. So typically, if they're clean and they're in good shape, they're not going to stick together. Once in a while, what we'll find is that steel, over time, as we use the equipment, may transfer into the electrode tips during the weld process. This may cause the electrode tips to stick to the workpiece or stick together. So maintenance is something that we'll discuss a little bit more in depth. There's a lot of different electrode tip styles like we see on the screen. And this is really a feature that allows us to combine it with different arm sets to provide access to different areas of the vehicle, different flange designs. Some of the equipment has removable electrode tips. In other cases, we have a dressing tool just to dress down the electrode tips. Taking a look at the spot weld arm sets that are available. We have a variety of different arm sets available, again, depending on the equipment and the design of that equipment. Some of these arm sets are insulated, especially where we have an arm set that's going to be reaching around a rear body panel or something of that nature. It's going to be important that we don't allow that arm set to short out against the edges of the body panels and things of that nature whenever we're activating this equipment. We want all of that current to flow through the resistance weld being made, and if the arm set's touching and shorting out to a panel edge or something, we're going to have potential damage to the panel edge or potentially a inferior quality weld. Some folks just opt to use like a fender cover or something like that over a panel edge that's in close proximity to where they're welding, and that helps minimize that issue. As we take a look at the top photo on the screen, we're seeing a couple different C-arm sizes. And one of the main advantages of the C-clamp style gun and arm set is that the applied pressure is not diminished with the different length C-arms. Some of the gun designs, what we've noted is that the really long arms require us to increase the inlet pressure, the input pressure to the cylinder to maintain tip pressure. And at a certain point in time, we may not be able to maintain the pressures to a degree that we'd like to with a really long arm set. So that's something to keep in mind as we're evaluating some of the equipment that we're looking at. My analogy here is kind of like a long set of locking pliers versus a short set of locking pliers, and sometimes we just lose that tip pressure that we need in those applications. The X clamp that we have in the center of the screen, this is an adapter that's available in the design of some equipment where gives us accessibility to different flange designs. And something else that we look at as we're evaluating equipment is how easy is it to change out the arm sets and get the tips aligned when we're out there in that production facility. As a technician, I want to keep things flowing. So again, this is something that for most equipment is relatively easy to do and pretty pain-free. The different types of arm sets on slide 17 here, and the different flange designs, really that's what it boils down to for the tips in the arm sets, identifying which ones are right for the different flange designs and applications. Most of our equipment manufacturers will have a quick reference sheet, which we'll want to keep with the equipment and handy and close by. This will help the technician identify the different arm and tip configurations for accessibility on that vehicle.
Jeff, how does the tip condition and alignment affect the spot welding process?
The electrode tips, it's going to be really important that each time the technician power up this equipment and start to put it into use, that we identify that the electrode tips are lined up with each other. And in most cases, they're going to come in 90 degrees to the workpiece. There may be some exceptions to that where we have a unique tip set or tip design or contact tip design on there for an odd flange on the vehicle. But they do need to align directly with each other. If they're offset or not in direct line with each other when they come together, we get our panels in between there, and now the current's not flowing directly through that panel. We can end up with an oblong-shaped weld, or in some cases I've seen where it actually blows holes in the panel. And, of course, that's counterproductive for us out there in the shop environment. Again, this helps us with proper current flow and getting a proper weld. The end of the contact tip diameter, with the amount of pressure and current we have being applied to these contact tips, over time, what happens with these contact tips is they'll very gradually start to mushroom out. The diameter of the electrode tip will tend to grow just a little bit. And this is something, again, the technician has to monitor in the operation of that equipment. And as that electrode tip diameter grows, more current's going to be required to produce the same quality weld. At some point, we have diminishing returns there. It's going to affect the quality of the weld. It's really what it comes down to. So again, the technician just needs to monitor this and make sure that we dress or replace the tips as necessary. Some of the signs that the electrode tips require attention can include poor-looking welds. If we get one bad-looking weld, we should stop and really evaluate what's happened there. Do we have molten metal thrown out of the weld? Is there steel buildup on the contact tips, which can cause those tips to stick? Or do we have severely discolored contact tips or electrodes? Again, maintenance is critical. I can't stress that enough.
For the equipment to maintain efficiency, proper cooling is essential.
Yeah, any type of welder, whether it's a resistance welder or a MIG welder or spot welding equipment, anything of that nature, has what we call a duty cycle. This affects how much work you can do before the equipment really needs to rest. Some of the equipment is air-cooled and some of it's liquid-cooled. So even with our liquid-cooled machines, they'll typically have a cooling fan that takes care of the electronics and some of the main unit items. But with the air-cooled units, what we find is that they'll use shop air to take and cool the cables and cool some of the other components in there. We want to make sure that we have, first and most importantly, clean, dry shop air that's being supplied to that equipment, and also that under our maximum shop demand conditions that we do have the volume of air necessary. It's not a tremendous volume, but again, if we're already working at max capacity with our compressors, we may have some minor considerations there to look at. The liquid cooling systems are really pretty impressive. On these systems, typically what we have is a circulation pump with some sort of a coolant, or maybe it's an antifreeze mix that's in there, and a coolant tank and a cap and level indicator. And this is a situation where they may, in some cases, circulate coolant all the way to the electrode tips on that equipment. So as we evaluate our equipment, we really want to look at what's our workload in our facility. Are we going to be working this equipment hard on a day-in, day-out basis, and we're really not going to be giving it a lot of rest? In most cases, that's not the situation, but there are some pretty high production facilities out there that once they start using this equipment, they want to be able to get that job done as quick as possible, and they may find that those liquid-cooled machines have some advantages in that department. And again, as I mentioned earlier, those electrode tips, they're soaking heat out of that weld, so if we have coolant flowing all the way to the tips, that can definitely be a plus for the weld process.
What are some of the more common machine settings, and how do they influence the weld?
There's a variety of different settings, and again, depending on the equipment, may influence what control you as the operator have over these. But in a nutshell, again, it comes down to clamping force is generally one of the adjustable items on there. And what we're doing here is essentially using a regulator to change the air pressure that's going out to that cylinder on that actuator, that arm set. And with this, what we'll do is we'll be looking to change the force applied to those tips. Some of the equipment we may have force in the range of 300 to 1,100 pounds. We're seeing some equipment that's even exceeding that. It's critical that if we look at the applied pressure to the tips, this is going to vary depending on the material stack that we have in there, the materials in there. We don't want to use the maximum pressure for every weld in every application. That becomes, I'm going to say, detrimental to the weld in some situations, and I want to say increased wear and tear on the tips and things of that nature. So we really want to try to identify what's appropriate for the metals, the different strengths of the steels. Are we weld bonding? And also keep in mind that this is not meant for joint fit up. We need to make sure those panels are together and mating up properly before we squeeze the trigger. The next potential variable we have there is current. This is going to provide the heat to the weld. So the amount of current is really something that may be in a program in the machine. Some of the equipment, whenever I tell that equipment the type of steel that it is and the thickness of that steel, that machine will come up with a baseline current that should be pretty close to what it's going to take to weld that material. In other cases, this may be programmable, and again, this is where we might be looking at some sort of an OEM recommendation or something of that nature to identify what the recommended amperage through that weld happens to be. The machine may give us a readout of what that weld current is. It may be as a percentage of the total current available, or more popularly what I'm used to is seeing that machine tell me how much current just went into that weld or is going to go into that weld. So that's pretty interesting to note. The next item that we may have is what we call the current on time. How long is current going to pass through that joint? And what this ultimately can affect is the weld size. If we take and we activate that welder and we're there making a weld and we're using a 60-cycle machine and it hums at me, and I'm not very good with sound effects, please forgive me there, but that machine's humming at me and I'm sitting there watching that weld being made. In some cases with that equipment, I can watch that weld nugget grow as I sit there and have my hand on the trigger and keep that welder in place. So a longer weld current makes a larger weld. There becomes, again, another point of diminishing returns here. Too much heat can be detrimental. And again, this can distort the tips, and in some cases it's actually creating a weaker weld because of the detrimental effects that heat may be having on that metal that we're welding. So a large heat mark around the spot weld can be an indicator that we've had too much time. With the inverter machines, we'll find that the weld time or the current on time is typically measured in milliseconds. And again, we typically can then go in a manual setting mode, and we can tune that up or down as we feel might be necessary based on testing. On machines without inverter technology, the time is typically measured and adjusted in terms of cycles of power based on the power coming in from our service. Again, remember that the inverter welder really makes it possible to apply, I'm going to say, more current over a shorter period of time when compared to most of the non-inverter technologies. Next thing we might have is the steel thickness as we look at a few more parameters here. Again, most of the equipment I'm familiar with, they typically have you measure one of the panels. We may have situations where the thickness is based on the combined thickness of all the panels, so it's going to be really critical that we know our equipment very, very well. But this is, again, typically a starter setting for that particular machine, and then we can tune it up or down slightly as necessary. It's typically given in millimeters. Different coatings that might be on the metal affect its electrical properties, so here we have to take that into account. And with a zinc setting, again, this is a very popular coating on steels, that takes and lowers the melting point and also lowers the electrical resistance. So we may have a pre-pulse of current that's applied to the zinc-coated steels. In other situations, we may have a call-out or a setting for heat-sensitive steels, such as our boron alloyed steels or dual-phase martensitics and things of that nature. This setting may have a more generic name, like a multi-phase as well. Whenever we take a look at this type of a setting, some of the equipment will institute a two-step weld, kind of a preheat, and then a second step to make the weld, or they may modify the slope up. They may ramp the current up or slope the current up and then taper the current off at the end of the weld. Again, the intention to help minimize the heat effect zone. Additionally, we may have weld bond settings. The weld bond settings can help account for adhesive between the mating surfaces, and we're going to go into more detail about this a little bit later on, but again, this is typically a two-step weld process. The first step to preheat, and that takes and burns through the adhesive. Additional settings may include a pulse setting or a soft start that may help to burn off any impurities in the weld zone. I'm really hopeful that the panels have been prepped properly and that we don't have impurities in there, but again, this is something that may be available on the equipment. Some additional things that the equipment manufacturers have for much of the equipment is vehicle maker information parameters that might be programmed into the machine or that might be downloadable and programmable into the machine. Again, giving us specific weld criteria and setting that machine up for specific welds on a specific vehicle. We're seeing where they're starting to incorporate some of the vehicle repair information in there as well, so this is really wonderful for our industry. Some other features that might be out there and some equipment have data logging. You know, if I want to take and I want to show proof that here's the welds that I did on this quarter panel on this repair, I can take and I can log those repairs. I can log each of those welds, and then I can download that, and I can print it out, and I can put it with the repair order file. That would be wonderful, wonderful documenting proof, if you will, that we did the right repair on this vehicle. You know, how do we know every weld was a good one? You know, that's a question. You know, something that the resistance welding process, the spot welding process, you know, there's a certain, I'm gonna say an assumption that, wow, we made a pretty weld, but is it a good weld? Not necessarily, and just like MIG welding. I can make a pretty MIG weld, but it may not be very strong at all. So some of the equipment will actually tell you right after you make that weld or as you're trying to make that weld that there's an issue with the setup or the metal stack, or there's something going on there that's just not right, and it may not even let you make the weld.
Jeff, could you talk briefly about machine capability and the latest technology available in Welders? Whenever
I get to talk with and work with the equipment suppliers and manufacturers and go to the trade shows and see the newest technology, I feel like, I got to say, a little kid in a candy store. It's really, really impressive. And the latest equipment that's really hit the market has the ability to basically sense the metals to be welded, and then based on the thickness and the resistance feedback information, it calculates the weld power that needs to be applied. So basically what we've got here is we set this equipment up, and there's a little bit of setup, and I'm going to say some calibration that's involved with this. But we take and we push the button, it brings those contact tips together, and it measures the thickness of the metal automatically. The unit then, it sends a current through that metal to try to identify what we're dealing with, and based on that pre-pulse of current, it determines how much current it's actually going to deliver to make that weld. Most of this equipment uses a transgun type technology to deliver the required current to the weld. I have to say, it's really impressive technology. Again, I do want to step back though and say no matter what technology machine you're using, it's still critical to make those test welds.
To get a good weld, the technician needs to be aware of important surface preparation procedures.
Yeah, absolutely. For current flow, we have to have a good conductive path between those electrode tips. And again, zinc coatings and weld-through primers, you know, typically these have zinc in them, and they'll usually allow current to flow. But some situations we may have E-coat or finished materials or sealers or adhesives or something else between those electrode tips, and this will usually prevent current flow. If we're preparing a part for spot welding, and we're not using any adhesives, generally we're going to take and we're going to remove the E-coat from the exterior flange at each weld location. We should really try to avoid taking any more E-coat off of there than we need to, but you need to take that E-coat off at each of the weld locations. Most cases we're going to leave the zinc coatings intact if it's a zinc-coated panel. Next, we may remove the E-coat from the inner mating flanges. Again, this may be based on vehicle manufacturer or equipment maker recommendations. In some cases, they may ask you to weld through the E-coat, but we want to leave that zinc coating intact. We want to make sure that the mating flanges are clean. And again, if we step back, and I have to reinforce here, make sure you're identifying what's the correct procedure from the vehicle manufacturer for the application that you are dealing with right now. In some cases, we may have recommendations to put weld-through primer in there. Others feel that weld-through primer is not warranted in that joint. So we'll take a look at that and do it on a case-by-case basis. When we're fitting up that joint for resistance welding or spot welding, make sure there's no gaps along the entire length to be welded. Make sure we've got our flanges straight, the panels are sitting in place properly, and that way we don't have any gaps that will cause excessive resistance or sparks to fly. If we have a shower of sparks coming out of our welds, we've got an issue with the setup. Something's wrong with that, with our equipment setup or our panel alignment or something of that nature. There's going to be some sparks that fly, but it should be minimal. We want to make sure we've got clamps holding those panels in place.
Even when the surface has been prepared perfectly, can you briefly cover some of the other influences that affect the weld?
Yeah, as I mentioned clamps on the last screen, we need to understand the electrical parameters of what's happening during this welding process. And I'm going to explain what a shunt is. A shunt is an alternative path for current to flow. When we're using clamps and locking pliers and screws and things of that nature to hold a panel in place, it's a really common practice for us out in the industry, but we need to keep those in mind and what they're doing to our weld current. So I'm going to explain just very briefly some basic electrical fundamentals. Current has got to have a complete path to flow. Current will flow through the path of least resistance, but there's one addition to that. Current is also going to follow any and all available paths, and it's going to divide up based on the resistance of each of those paths. So as we take and we use a clamp to complete the circuit for a weld, we call this shunting the current. This is beneficial, and it's required whenever we have no metal-to-metal contact. If I'm putting panels on and I've got E-coat between the flanges, or if I'm weld bonding with adhesives between the flanges, I need to shunt that first weld. It provides that initial path for current to flow, and once I've shunted that first weld, I really don't need to shunt any more welds on that flange. Again, this is a situation where we still need to remove that E-coat from the outer surfaces, at least where the electrode tips are going to come into contact, and again, shunt that clamp at the contact workpiece on that first weld. Now, as we move on to the next slide, once we've shunted the first weld, typically we do not want our other clamps to shunt the weld current on that flange. So it's a good practice to take and maybe wrap some electrical tape around those clamp jaws to keep those clamps from, I want to say, stealing our current. The dedicated shunt clamps are available, designed for the shunting purpose. We see a pair on the screen there. Again, we want to make sure that the panel is fit up properly and we've got clamps in place, but we don't want those clamps stealing our weld current. Something else, though, as we move to a different flange on the same vehicle, we may find that initially we need to shunt that first weld on a different flange on that vehicle.
Can you briefly explain why test welds still are necessary?
Absolutely. We have such a variety of different potential combinations of materials and coatings and things of that nature that we deal with out there in the collision repair industry on a day-to-day basis, that really to ensure that we're obtaining proper machine settings and that we know 100% sure that we've got good quality welds, we should make test welds before welding on that vehicle. We want to make sure as we're doing these test welds, we are duplicating 100% the same conditions as on the vehicle. The metal types, the thicknesses, the number of panels, the coatings, adhesives, things of that nature. And for the most part, we want to try to keep realistic, I want to say, distances from the panel edge and things of that nature. So the stack and makeup have to all be the same. As we start to look at this and we make those test welds, the size of the weld nugget can vary depending on the thickness and the type of the metal that we're dealing with. A good general recommendation for a minimum spot weld nugget size is 5 times the thickness of one workpiece. Some vehicle manufacturers have very extensive spot weld parameter guides where they identify what they're looking for in the actual performance of these welds. So it's a good idea to check those out as well. There may be recommended nugget diameter charts that address this. Now, in order to determine the size of the nugget made, a sample weld typically will be either twisted or peeled apart. And on the left side of the screen, we're looking at what we call the twist test. And on the right side of the screen, we're looking at what we call the peel test. Depending on the parameters and the type of material and the thickness, we would expect to see nugget tear out on one of those pieces of metal. But we have to be real careful here. With some of the advanced high-strength steels, and especially some of the ultra-high-strength steels, the brittleness of some of these materials, as we start to get up into some of these advanced materials, we're finding that we don't always get tear out. Most of the time we do, but there are some situations where we might not. So it's really a factor of the material type and thickness. As we're looking at these vehicles, as we're repairing these vehicles, we're disassembling them, we're taking them apart, we're removing damaged structural components. We need to examine the structure of that vehicle, look at the damaged areas, the areas of direct damage and the areas of indirect damage, and evaluate how did the OEM spot welds hold up. And as we're tearing that vehicle apart or disassembling that vehicle, removing those structural parts, it's a good idea to take and maybe do some destructive tests to evaluate the OEM welds, see how they perform. I would think we'd want to expect to see similar results on our replacement welds. Again, there's so many variables out there that we really need to take the time to do the setup and testing. The ultimate test of welds, as we take a look at slide 27 here, would be what we call a lap shear test. Now lap shear test equipment is not really very practical for collision repair facilities. So with a spot weld, as we look at that weld, we can't say, hey, it's a good one just by looking at it. Much of the equipment will take and tell us electrically what happened in that weld if we have equipment that has the ability to give us that printout and log those welds or tell us about the quality of each weld we just made. But again, a destructive test is ultimately the best way in that typical shop environment. So looking at that twist test or that peel test, we need to evaluate what's going to be correct. In most cases, the twist test might be appropriate, but in some cases, the peel test plays out as being better, and we'll take a look at that here in just a minute. If you don't test your welds, I have one question for you. Who's gonna? Is it going to be your customer in the next collision? Hopefully they do okay.
Okay, at this point, in order to allow some time to have some questions at the end of this, we're going to skip ahead a little bit to slide 35 about the ICAR WC-SO4 live demo class. I understand that ICAR will soon be making some enhancements to its spot welding class. Is that right, Jeff?
Absolutely. The collision repair industry has provided a lot of feedback, and what they've basically told us is they want to see live demonstrations involved with ICAR classes. And so ICAR has taken the squeeze-type resistant spot welding course, the WCSO4 course, and we're going to incorporate live demonstrations in conjunction with the traditional class presentation. We conducted a pilot at River's Edge Collision Center in Milford, Ohio. We had the pleasure of Bill Montville coming down from Collision Correction Equipment and providing live equipment demonstrations, and Dave McKinney is one of our instructors out in the Ohio area. He led the presentation. We really appreciate the support and valuable feedback we got from those folks that attended that and for the folks that supported that. On May 21st, ICAR is going to integrate those live demonstrations into the classroom-led course that we have. Essentially, the course will be conducting live demonstrations at various points during the program presentation, identifying proper equipment setup, aligning, maintaining electrode tips, making the spot welds, destructive testing, more details on a lot of what we've talked about here today.
Okay, we're going to skip our final polling question and just move ahead to the Q&A session. We'd like to take this opportunity to solicit questions from our viewers. If you have a question to ask, simply type it up and send it to us through the channel provided. We already have our first question on tap, and that is, how does the metal stack affect destructive testing?
The metal stack plays a critical role in that destructive test and the evaluation of what should happen. We may have a situation where we have mild steel, high-strength steel, and a piece of ultra-high-strength steel in the same stack. And I would certainly expect to see metal tear out from that mild steel, and most likely we're going to see that metal tear out from that high-strength steel. If I were to take and I were to see metal tear out in that metal stack from the ultra-high strength steel, I might start to question that maybe I was putting too much heat into that weld and I was overheating that ultra-high strength steel, compromising it. So again, we may then step back though and look at situations where we have a couple of pieces of ultra-high strength steel in that metal stack. And because of the nature of that ultra-high strength steel, we may not necessarily see a tear out on that destructive test. Again, this is something that's critical for us to keep in mind as repair technicians and as an industry as we repair these vehicles.
Do you need to do a test weld with a smart welder if you have the OEM spec?
Absolutely. What they really can't account for is the potential variables at the actual site. Did I really prep it properly? Are there potential contaminants in there that, there's just so many things that on a given day might be slightly different. And so this is where we strongly encourage folks to do those test welds, even with the latest and greatest technology.
Can you address the different size tips, for example, 13 millimeters versus 16 millimeters used by different welder manufacturers? What's the difference?
It's really up to the equipment manufacturers as they design their equipment as to the finish, I'm going to say tip design, shape, etc. Usually at the actual contact point, we don't see a huge difference in the weld nugget, although, again, depending on the technology of the machine, we may see some variations there.
Can you explain the difference between the adhesion and fusion process?
That steps back to essentially MIG welding and oxyacetylene process, where with any type of fusion welding, you're joining the base metals with a similar metal, if you will, and with an adhesion process, that's more like brazing, where you have a dissimilar metal that through capillary action is adhering to the surface of the panels, joining those together, and it usually is, I'm going to say, a softer joint.
I've heard that training is very equipment specific when it comes to spot welding. Is that due primarily to the advancements in welder technology?
I think it really is in the subtleties of how the equipment manufacturers, I'm going to say, engineers set up and design their equipment, and how they felt was the most comfortable way to go about it. So far as the technology involved, there are some aspects of that impact and are going to be implicated in how the equipment's operated. So it is vitally important that the technicians that are going to operate this equipment, they are really, really thoroughly educated on the operation of the equipment, every aspect of it.
Do some OEMs recommend using MIG along with spot welding when there are more metals to be joined together?
I've looked through a lot of different OEM repair procedures, and I've seen procedures where parts, structural components especially, are being replaced on vehicles, and I see procedures that map out where we're going to use resistance welds in certain locations, MIG welds in other locations, and in some cases adhesives in other locations. So again, it really becomes one of those areas that it depends on the specific procedure from the vehicle manufacturer. Some of that question may stem back to the earlier days of resistance welding. If I take it out of context, I want to be very careful here, but I know early on, whenever some of the equipment that had limited capability came to market so far as spot welding, the faith, the trust just maybe wasn't there, and so they said, well, you can use that resistance spot welder, but you're still going to put some MIG plug welds in there. So again, I want to make sure I don't get that out of context. But today, for the most part, it's accessibility that drives a lot of that need to use a MIG welder in a repair procedure, not necessarily limitations of the equipment.
What is a safe distance for a clamp to be from the weld so you don't get a shunt?
I would look at the weld spacing recommendations from the vehicle manufacturer and typically try to replicate that type of spacing for the shunt clamp versus the weld location.
Is spot welding going to become the standard for the repair process like MIG welding did in the 80s?
I see it being one of the highly recommended and preferred procedures required by some vehicle manufacturers in some applications, but there's still too many other processes out there, and we're seeing situations where vehicle manufacturers are looking at rivet bonding for steel components in some vehicles, and again, if that's their recommendation or requirement, that's the direction we should go.
Is a MIG tack weld always necessary in most spot weld repair jobs?
In situations where if somebody's used a MIG tack weld, they may have used that just to take and temporarily hold that panel in place while they're getting other things set up. That MIG tack weld actually becomes a shunt for that first weld. So again, we probably wouldn't want to have a lot of MIG-Tech welds around because that may be detrimental to what we're actually trying to achieve by using the resistance welder. But that MIG-Tech weld may affect that shunt effect for that first weld for us.
Where can single-sided welding be used, and where does the OEM stand on this?
To the best of my knowledge, single-sided welding, we have some really severe limitations on the ability to apply enough force. And for the most part, it is not a recommended procedure. That would be a subjective business decision in a non-structural application. I would be very, very cautious in applying single-sided spot welding techniques to a vehicle structure.
Is adhesive material required for the weld bond technique, or is just a sealer or weld through good enough?
If the vehicle manufacturer is indicating that we should be weld bonding, and they're probably leaning towards an adhesive, a structural adhesive material, we need to get that material in there to get maximum advantage of that material. Those adhesives are extremely strong and contribute greatly to the strength and performance of that vehicle structure in a subsequent collision. Sealers do not nearly approach the strength properties of those adhesives.
Once the equipment and surface prep have been set up, how long does the actual weld process take once the trigger is pulled?
In most cases, the actual weld is a very short process. In some cases, we've got the weld completed in a few seconds, and then we're moving on to the next weld. It's really a pretty production-oriented process.
Why is it that the new smart welders with trans guns do not have single-sided guns?
That I'm not too familiar with. I'd have to defer to a conversation with one of the equipment manufacturers so far as the limitations on that. I'm not sure if it's inherent in the technology or if there's some other aspect to that. So.
And our final question, can you spot weld over original factory locations, or will you have a weaker weld?
There are some applications where the OEM, the vehicle manufacturer, may guide us to weld over an original location, but it's very rare. It's few and far between. Again, this is a situation where in most cases we're going to identify a location adjacent to the original weld location for our replacement weld. Where this gets a little sticky is where if we have inner structure and multiple layers of metal and we're only putting on an outer panel, and if you have weld bonding in that original construction of that vehicle, you may find you've got some challenges when you try to resistance weld that panel on and use a new location. So we want to try to evaluate this very early on in our repair process and our welding of that panel back on that vehicle to see what kind of challenges, see what kind of recommendations there are, and make sure we've got success.
Thank you, Jeff, for presenting this information. And once again, thank you to our sponsor, ProSpot, for their support. If you'd like to view this webcast again or share it with somebody who is unable to participate today, the webcast will soon be archived at www.abrn.com/spotwelding. Once again, that's www.abrn.com/spotwelding. Thank you.